starting. Is it visible to you now?
No, it is not visible.
Okay, I'm started sharing now.
Yes, now it is.
It is okay. So, hello everyone. Thanks for inviting me to this outstanding conference. Today we are going to discuss a very interesting topic about addictive substances, which is the post-mortem analytical challenges that we face. I'm Ghadeer Abdelaal, Forensic Medicine and Toxicology Senior Lecturer at Faculty of Medicine, 𝒂𝒅𝒊𝒄𝒕𝒊𝒐𝒏, a Fellow of the Egyptian Forensic Medicine Authority in Cairo, a founding member of 𝒂𝒅𝒅𝒊𝒄𝒕𝒊𝒐𝒏 Forensic and Clinical Toxicology Research Laboratory, also a founding member of the Safe Women Clinic in 𝒂𝒂𝒃 University Hospital. Prepare yourself for a mind-opening exploration into the complex world of postmortem toxicology, where the truths not always align with our initial assumptions. What if I told you, okay, is the presentation visible to you? Okay.
Yes, it is.
Okay, what if I told you that the post-mortem concentration of addictive substances may differ from their levels at the time of death? Actually, this is the challenge that we face in post-mortem toxicology. The post-mortem analysis of addictive substances is of critical importance for forensic investigations to understand the causes of death related to substances of abuse. However, the detection and the quantification of these substances in post-mortem matrices present unique challenges. These challenges are post-mortem redistribution of drugs, decomposition of tissues, drug degradation, and the complexity of sample matrices. Let's begin with the first and the most important one, which is post-mortem redistribution. Actually, changes in drug concentrations after death may occur due to several mechanisms. The first one, which is the primary cause, is the passive diffusion from reservoir organs along the concentration gradient. The second one is the post-mortem cadaveric changes, for example, hypostasis and cellular acidification and autolysis. Actually, cellular acidification can cause accumulation of basic drugs in tissues and decrease the protein binding properties of some drugs. Also, putrescent bacteria can metabolize many drugs. The third mechanism is, or the third factor is the post-mortem interval, where redistribution tends to increase with time. And last or finally, the drug properties, generally lipophilic, basic, highly protein-bound drugs and those with high volume of distribution, more than 3 liters per kg, are particularly susceptible to this redistribution. The second challenge that we face is the decomposition of tissues. Actually, decomposition has two phases. The first one is autolysis, and it is an enzymatic process, and the second one is a putrefaction, which is a bacterial process. The released hydrolytic lysosomal enzymes are activated in the acidic intracellular environment after death and cause breakdown of cellular materials, resulting in the release of drugs from cells into the extracellular compartment. The second phase is a putrefaction, where bacterial degradation of matrix proteins and lipids results in putrefactive byproducts, which can interfere with the analysis of drugs, particularly with less selective detectors. Also, bacterial degradation of the drugs themselves can lead to changes in their concentrations or even complete loss of some analytes. The third challenge is a drug degradation. Due to several mechanisms, for example, the residual enzymatic activity, as some enzymes continue to operate after death, And here I want to emphasize that the beta-glucuronidase loses its activity slowly, and it is vital to the forensic toxicologists as it can convert glucuronide metabolites of some drugs back to their parent drug. The second mechanism is the decomposition. Some drugs are unstable either from the pH changes after this or from their use as a substrates by vitrofactive bacteria or combination of the above. And the inadequate storage and analysis may lead to drug degradation as well, as drug levels may also change during the post-sampling period while samples are inadequately stored, or during the analysis, thermal degradation in the GCMS injection port. The fourth challenge that we face is the complexity of sample matrices. Forensic toxicology investigates the presence of drugs in autopsy cases using a wide range of sample matrices that may result in a matrix effect of complex specimens that affects the ionization of the analyzed and hence their detection. And the byproducts of decomposition. They are more extractable, lower molecular weight compounds than the drugs, which can mask or alter the presence of drugs in biological samples, particularly with the less selective initial screening techniques such as immunoassays. To sum up the postmortem toxicological challenges that we face, the postmortem redistribution of drugs, the decomposition of tissues, drug degradation, and the complexity of the postmortem sample matrices. How to overcome these challenges? We can do appropriate sampling and adequate storage. Also utilize advanced selective analytical methods. Peripheral blood samples are preferred, being less affected by the post-mortem redistribution and should be collected as soon as possible. And we should avoid blood from sites with putrefactive signs such as marbling of vessels or gas formation, as they will contain bacteria that can affect the toxicology results even with preservatives. Therefore, liver or other tissues are often used in such cases of putrefaction. For drugs known to undergo postmortem redistribution, multiple samples are recommended, as peripheral blood should be analyzed in preference to central areas for estimation of the central to peripheral blood ratio and liver to peripheral blood ratio. Actually, CP ratios more than 1 indicates the occurrence of postmortem redistribution, as well liver to peripheral blood ratios more than 20 indicates redistribution. Appropriate storage. Although it is not possible to control postmortem microbial action or redistribution of drugs, chemical preservatives can be used to inhibit further degradation of drugs after collection. Also, filtration sterilization is a method of removing bacteria from urine samples by filtering them through a 0.2 micron membrane. This has been shown to inhibit drug loss in urine samples due to bacterial action. Also, specimens should be stored at appropriate temperature at or below minus 20 degrees Celsius. Well, the third precaution is to use advanced selective analytical methods. Putrefactive compounds can interfere with many analytical procedures, such as immunoassays, making drug detection challenging. To address this issue, more selective techniques such as GCMS and LCMS are being applied. They have some limitations, such as the thermal degradation in GCMS injection port and the matrix effect with the liquid chromatography mass spectrometer. These obstacles make specimens difficult to evaluate without selective detection methods. As the GCMS is limited to thermally stable, volatile, non-polar compounds, the LC tandem mass spectrometer has been considered as a new gold standard for its ability to identify more diverse types of analytes, polar and non-polar compounds. However, it is not suited for non-targeted analysis. Ion mobility spectrometer can detect 1 part per billion, and it is very selective, thus it can detect isomeric compounds. And the most important one is a high-resolution mass spectrometer, which has advanced the non-targeted comprehensive approach for drugs of abuse, including newly psychoactive substances. It has an accuracy of 0.001 atomic mass unit, thus it can discriminate isomers. Well, again, to overcome the postmortem toxicology challenges, we have to use appropriate sampling from especially peripheral blood as soon as possible, and do adequate storage at -20 degrees Celsius with preservatives, and finally utilize advanced selective analytical methods. Now let's dive and explore peers of postmortem toxicology investigations of the most common addicted substances. The extent of opioids redistribution can vary based on individual drug properties. Highly lipophilic opioids such as fentanyl and methadone have a greater tendency for postmortem redistribution compared to less lipophilic opioids. Regarding stability, heroin is rapidly hydrolyzed to 6-monoacetyl morphine within minutes of use, and this metabolite is unstable in aqueous alkaline solution and is rapidly hydrolyzed to morphine. Once morphine in the liver, it is metabolized to morphine 6-glucuronide and the morphine 3-glucuronide. This photo demonstrates the metabolic pathway of heroin, and the last two metabolites, glucuronide metabolites, can convert back to their parent compound, which is morphine, in unpreserved tissues. And this process is hastened by factors such as temperature and bacterial contamination of the specimens. Due to the instability of metabolites and the inter-subject variability, determining the ratio of free to total morphine may be compromised for specimens that are contaminated with bacteria, exposed to sunlight as it is light sensitive, and in biological matrices that contain beta-glucuronidase enzyme. And inadequately stored samples, as samples should be stored at -20 degrees Celsius in the dark. Let's move to the stimulants and begin with cocaine. Heart blood should never be used for quantitative analysis of cocaine, as cardiac muscle have high concentrations relative to blood, and these concentrations, a high concentration gradient, may make cocaine diffuse into the cardiac blood. Spontaneous degradation of cocaine to benzoagonine may happen under alkaline condition, and residual cholinesterase activity in biological specimens may convert cocaine to agonine methyl ester, which in turn is degraded to agonine. And this process is inhibited by adding 1% sodium fluoride to the samples as preservative. When cocaine is combined with ethanol, cocaethylene is formed, which is more stable than cocaine. However, cocaethylene still degrades in biological specimens. Another issue here is the likelihood of bacteria creating cocaethylene as well from cocaine and the post-mortem produced ethanol, not from the ingested ethanol. So we have two sources here for the metabolite cocaethylene. It might be from ethanol co-ingested with the cocaine, or from the post-mortem production of ethanol, as it may produce post-mortem. Amphetamines being basic lipophilic drugs, both methamphetamine and amphetamine may undergo post-mortem redistribution. Both are stable with no significant changes occurring in their concentrations in stored samples. Sedatives. Let's begin with the benzodiazepines. Benzodiazepines may as well undergo postmortem redistribution. Regarding stability, diazepam is stable, while nordiazepam and fluorazepam are moderately stable with only minor losses in blood and tissues. However, chlordiazepoxide and norchlordiazepoxides are rapidly degraded to various metabolites, thus unstable. Regarding barbiturates may as well undergo postmortem redistribution, and they are unstable in alkaline solutions. And here we have to emphasize that putrefied samples are known to become alkaline during decomposition. The gamma hydroxybutyric acid is a club drug and called a date rape drug, as it may facilitate rape. So it's of critical importance to in forensic investigations. It may undergo post-mortem redistribution, and it is present as an endogenous compound in the ante-mortem samples at concentrations of 10 mg per liter in urine and 4 mg per liter in blood and plasma. However, higher concentrations up to 433 mg per liter have been found in unpreserved postmortem blood, indicating its production in vitro. However, preservatives and freezing minimizes gamma hydroxybutyric acid production in vitro. Finally, alcohol. Well, ethanol may undergo postmortem redistribution, and it can be produced post-mortem, as we mentioned before, due to the bacterial action, which results in concentrations as high as 1.5 mg per milliliter in tissues. In case of postmortem ethanol production, the ratio of serotonin metabolized will be below 15. Ethyl glucuronide is an ethanol ingestion metabolite. However, it can be produced in urine samples contaminated with E. coli and gives false positive results of ethanol ingestion. However, there is another ethanol ingestion metabolite, which is ethyl sulfate, that is not affected by the E. coli, so it is preferred. My take-home message for today is understanding the post-mortem analytical challenges is crucial for accurate interpretation and determination of the role of addictive substances in post-mortem cases. Thank you. If you have any questions, I'd be glad to answer them now, or you can contact me on my email, ghadeer.mma@gmail.com. I'll post it in the chat box. And thank you for everyone for all the audience and for the organizing committee for inviting me to this talk, and especially to Jennifer, the one who contacted me, and a very kind person, and her prompt response. Thanks to everyone, and to you, the host. Thanks.
Yeah, thank you, Ghadeer Abdelaal. Thank you for the presentation. Yeah, any questions, please? Yeah, any questions to Ghadeer Abdelaal? Yeah, I think there is no questions. Please text your email ID here in the chat box. If they have anything, they will contact you and you can respond back to them on email.
Yes, I texted them.
Yeah, thank you very much, and thank you for joining us. Thank you. Yeah, without any further delay, we'll move on to our next presentation. And I call upon Dr. Emilia Baril from University of Bologna, Italy, to give her lecture on philosophical views on interoception.
May you hear me?
Yes, Doctor, yes. I can hear you. Please share your PowerPoint presentation.